The density at any point on a semicircular lamina is proportional to the distance from the center of the circle. Find the center of mass of the lamina. All right, there's our lamina represented on the xy plane. And you can see our x squared plus y squared equals a squared. That's the formula for our circle. We have just half of that as one of our boundaries, and the x-axis as the other. And one thing to note here, if we're going to be talking about center of mass, is given the fact that we have the density proportional to distance from the center, as we extend outward on either side in either quadrant 1 or quadrant 2, we're going to have mass evenly distributed on both sides of that y-axis. And so this is important for us to know because it means that our work in finding the x-coordinate for our center of mass is already done for us. It's going to be 0. It has to lie somewhere along the y-axis because of the symmetry. Okay, so there's our semicircle, and you can see it intersects the x-axis at negative a and a. And the distance from 0 of any point xy is the square root of x squared plus y squared. We're going to use this because we have our density function as a constant times that distance. We were told that our density function is proportional to distance, so k is our constant of proportionality. So we have our rho equals k times the square root of quantity x squared plus y squared. Now we want to convert to polar coordinates. Anytime we are dealing with a shape such as this one, a circle, a semicircle, something with leaves, we know that polar coordinates are very well suited to our calculations. So we use our conversion equation, r squared equals x squared plus y squared, to get r equals the square root of x squared plus y squared. Or rather, we had the square root, and we're using it to get to r. We're going in the other direction. And we have our domain suggested by r being between 0 and a, and theta lying between 0 and pi. And our mass as a double integral. It's the double integral of our density function with respect to area. And we can substitute in our constant times distance. And then in polar terms, our constant times distance is that kr. And our dA, the area element, is r dr d theta. Okay, we can factor out the k. And we can actually rewrite this double integral as a product of two integrals. And that way we can take both integrals simultaneously. Well, not exactly simultaneously, but side by side, and then multiply the results. And so we go ahead and do so. And you can see when we integrate from 0 to pi d theta, we get theta evaluated at pi and evaluated at 0. We wind up with pi minus 0, or simply pi. And once we've done the second antiderivative, you can see easily it's a r squared goes to r cubed over 3. And we get k times pi times a cubed over 3 for our mass. OK, so we have our mass. We want to find our center of mass now. We did already find the x-coordinate. We found the x-coordinate was 0 by symmetry. If we were to look at the graph of this, we would see more clearly that because we have a semicircle and because our density function is constant, or is proportional to the distance away from the center, we're going to have mass evenly distributed. And so in that case, we'll have our x-coordinate as 0. And our y-coordinate of the center of mass is given to us by this formula. We're taking the reciprocal of mass, double integral with respect to our domain D of y, the distance from the x-axis, times rho, the density function with respect to a. And so you can see we took our mass that we had found in the last screen and flipped it over, since we're taking 1 over the mass. We cancel out a k up top and a k below. And we'll have 3 over pi a cubed left as a factor outside the integration. And again, we can rewrite our iterated integral as a product of two integrals. And we can anti-differentiate and multiply, and we find that y bar, the y-coordinate of our center of mass, is equal to 3a over 2 pi. OK, so looking back to our graph, And so our center of mass lies along the axis of symmetry, the y-axis.